Good morning, my dear student. Today we'll be talking about the integration of a sequence of non-negative measurable functions. So then we'll be proving two results, smaller results, using the consequences of Fatau's lemma. We know we have already proved the Fatau's lemma. Using that Fatau's lemma, we have defined the third definition of integration like this. So the last theorem we discussed was, so f is a non-negative measurable function. Then what we got in the last theorem is that there exists a sequence of simple measurable function phi n which is monotonically increasing, and phi n converges to what f. So this we have discussed in the last theorem. Then using this theorem, you can get the definition of integration of a non-negative measurable function like this. So definition, integration of f of dx is equal to, so since the sequence is monotonic increasing, so limit n tends to infinity, this is integration phi n x dx. The first consequence of Fatau's lemma that we already proved, this is equal to, so this limit can go inside the integration, limit n tends to infinity, phi nx dx. So, and then using this theorem that for a given non-negative measurable function, we will be always able to find a sequence of non-negative sequence of simple measurable function such that the sequence of simple measurable function is converging toward the function f, and it is monotonic increasing also. So then using the first consequence of the Fatau's lemma, integration of this function is equal to limit n tends to infinity phi n dx. So then this n can go inside limit, this limit can go inside the integration, then you get so this is what, this is this one, okay, this is this one. So therefore integration of a non-negative measurable function can be defined like this also. So for every such non-negative measurable function, you will be able to find a sequence of simple measurable function which is monotonic increasing, and it is converging toward the function f, and then this equality holds. So this is the third definition of integration. Okay, the first definition, the second definition was what? The second definition is integration f dx, this is equal to supremum of phi which is less than equal to f, and integration phi dx, because the first we define integration for simple measurable function, then we define this integration for a non-negative measurable function like this one. Okay, so this is in terms of supremum of the integration phi dx, where supremum is taken over all simple measurable function phi such that phi is less than equal to f. So this was the definition, second definition. So now this definition can be replaced according to our convenience by this definition. Okay, so this is all about this definition is possible because we prove Fatau's lemma. Alright, so from Fatau's lemma we get a small result. Okay, using that result, now you can define, integration of a function like this. Integration of a non-negative measurable function f can be defined like this one, because for every such simple no, for every such non-negative measurable function, we are going to get a sequence of simple measurable function phi n, which is monotonic increasing and which is also converging to the toward the function f. So using the Patau's lemma, then you can easily establish this equality. So this is how we define the third definition of integration of a non-negative measurable function. Okay, so this will be more convenient in the later part of the remaining part of the theories, okay, to use this one. All right, so now then let us come to the main theorem of today's lecture. So let f and g be non-negative measurable functions. F and g are non-negative measurable function. Then so sum of the integral of this function f and g is equal to integration of the sum function f plus g dx. Right, so this is the one. This also this theorem can be proved by using the second definition and the third definition. Okay, so the third definition will be more convenient here, so we will be using the third definition. So you can prove it by using the second definition of integration, okay, of a non-negative measurable function. So you try for that one, which is second definition. Let us now use the third definition. Okay, so let phi and psi be simple measurable function such that this is, you can use second definition also, such that phi is less than equal to f and psi is less than equal to g. Then since phi is a simple measurable function, you can write phi in this form: phi is equal to summation I running from 1 to n ai chi ai. What is capital AI? Is x, the set of point x, such that phi of x is equal to small ai. This is small ai. And you can also write psi in this linear combination form of finite characteristic functions. Okay, j running from 1 to m bj chi bj, where bj is the set of point x such that psi x, this is psi x, is equal to small bj. So you can write phi and psi in this form, and we already knew that this these capital AIs are disjoint sets. All right, we have already established, and since the domain of integration is the set of real number r, this r is equal to this disjoint union of finite set AIs, I running from 1 to n. So similarly also, so bj's are disjoint sets. Okay, so r is a disjoint union of m such disjoint set bj's. Okay, so then again you can easily establish this one. All right, then r is equal to how much? R is equal to I union I running from 1 to n union j running from 1 to m ai intersection bj's, and this is again a disjoint union of nm sets ai intersection bj's. Okay, so this thing you can easily understand. Okay, you try to find this one. If you have some confusion, then you can talk to me also. And then so the 5 plus psi takes the value ai plus bj in the set ai intersection bj's. Okay, so then 5 plus psi is equal to summation I running from 1 to n summation j running from 1 to m ai plus bj. You can write and this is again a simple measurable function. All right, so for simple measurable function we have already proved this result. For simple measurable function we have already proved this result. All right, so that means sum of simple function integration over the domain ai intersection bj is equal to integration of phi over the domain ai intersection bj plus integration of psi over the domain ai intersection bj's. All right, so this is already we have proof for simple measurable function. Okay, and then so from here using this one, integration on r is equal to integration on r means what? So r can be written as union I running from 1 to j and and sorry, union I running from 1 to n, union j running from 1 to m, ai intersection bj, that is equal to r. Okay, so that is equal to sum of this sum of these two integration. So that means what? Ultimately you will get this one integration, here r is here. All right, so here the union r will be here, here r will be here. Okay, so ultimately what you get, integration of the sum of simple measurable function phi and psi is equal to integration of the phi plus integration of psi. Okay, so this you can easily establish. All right, so then what this then you think about the sequence of function, simple measurable function phi and psi n. So now we are going to use third definition of integration. So let us take two sequences phi n and psi n of simple measurable function, and they are also monotonic increasing and converging toward the function f and g. Phi n is a monotonic increasing sequence of simple measurable function converging to f, and psi n is a sequence of simple measurable function converging to g. Okay, then it is easy that to see that phi n plus psi n is another sequence of simple measurable function which is converging to the function f plus g. All right, so according to this result, this is what sum of the simple measurable function integration is equal to this integration plus this integration. Using this one in phi n plus psi n, you will get this one. So integration of phi n plus psi n dx is equal to integration phi n dx plus integration this is psi n dx. So this one. And then if you take limit, again property of limit, if you take limit n tends to infinity, you take limit n tends to infinity in this part plus limit n tends to infinity in this part. Okay, so then what you get? So then it is straightforward. So this limit according to that consequence of the Fatau's lemma, this limit can go inside the integration. So when it goes inside the integration, limit n tends to infinity phi n plus psi n is equal to f plus g. So let me write there. Let me write here. So what you have is limit n tends to infinity integration phi n plus psi n, this dx is equal to limit n tends to infinity integration phi n dx plus limit n tends to infinity integration psi n dx. This equality you have. So using that theorem, this limit can go inside this integration. So that means what? It is equal to limit n tends to infinity phi n plus psi n dx. You get this one. This is equal to this one also, you can go inside the integration. This is limit n tends to infinity fn phi n dx plus limit n tends to infinity, this is also inside integration, so psi n dx. You will get this too. But when n tends to infinity, phi n plus psi n goes to f plus z. So this is f plus z dx, and this side also, when n tends to infinity, limit phi n is equal to z, f, this is f dx plus here also z dx, you will get this one. So this is what we wanted to prove. Okay, so easily using definition 3, the third definition, now we are able to establish this, equality. Okay, so now then let us go back. Lastly, let us prove this result. So the above result can be extended to a sequence of function. Okay, sequence of function. The above result is only for two functions f and g, but if you have a sequence of function fn, then what you have this one, integration sum of this function n going from 1 to infinity fn dx is equal to, you can take out the summation outside the integration, n going from 1 to infinity is integration fn dx. Okay, so this equality, so that means the summation can go inside the integration, it can take outside the integration, they are equal. So what is the theorem? Let fn be a sequence of non-negative, it should be non-negative measurable functions, then this equality holds. So it is very simple, just using extending the above result to infinite cases. So by induction you have proof for two functions. Okay, we know that integration of f plus g is equal dx is equal to f dx plus g dx. Okay, for non-negative measurable function f and g, we know this result, just we have proved that one. So by induction it can be extended to the finite sum from 1 to n. Okay, so by induction what we have is that summation I running from summation I running from 1 to n fi dx integration is equal to, you can take out summation outside integration I running from 1 to n integration fi dx. Okay, so this equality holds, it is obvious by induction. Okay, and then you can put this one as equal to Sn, you can put this one as equal to Sn, so this is Sn. All right, summation I running from 1 to n fi dx. Then what is Sn? It is a sum of positive number because it is non-negative function, so this is sum of positive number. So Sn plus 1 will be one more term than Sn. No? That term is non-negative also. So what I want to tell you is that this Sn is a sequence of increasing, it will be a sequence of increasing, okay, a sequence of increasing non-negative function. Okay, it is obvious that then it is increasing. No? So since increasing, and it is obvious that this Sn converges towards f. What is f? F is equal to I running from 1 to infinity. Okay, the sum of all the sequence function. Okay, sum of all the function when n tends to infinity. So limit n tends to infinity, Sn is equal to summation I running from 1 to infinity fi. It is obvious. It is obvious, and it is monotonic increasing. Sn is a sequence of monotonic increasing function. Okay, so you get this one. So then again we are going to use Fatah's lemma again, so many times. Again use, if you have such sequence, then limit n tends to infinity is equal to, you can go inside the this one, and you can go inside the integration. This is outside, limit n tends to infinity is equal to this limit. If you go inside this integration, you will get this one. Okay, so that means limit n tends to infinity, this one. All right, so that means what? That means what? I running from 1 to infinity, this limit as limit n tends to infinity, Sn is equal to what? I running from 1 to infinity fi dx, this equal to. Okay, so ultimately what you have, the summation, this summation, okay, so if you take out from the integration, they are equal. All right, so it is very simple, but they are starting point, but we have used Fatau's lemma very frequently and its consequences. All are consequences of Fatau's lemma. The third definition is also consequence of Fatau's lemma. And then, another very important consequence also we have been using again and again. So that's why I told you Fatau's lemma is very important. Try to understand completely, and then you watch the videos again and again. So yeah, this much I want to give to you for today. I'll come back tomorrow with more results and examples, interesting examples. Okay.